How was lunch?
Great.
All right, did you really good job down there in the cafeteria. So yesterday and this morning, we covered data acquisition. Now we're going to roll into 3D. All of you got these great new scanners. You probably haven't been, well, who's been doing 3D so far? So a couple of you. So those of you that have not been doing 3D, you got these new scanners, and your doc is going to come up and say, I want to do a 3D. And you'll say, okay, what do you want? He'll say, well, I don't know. What can you do? You say, well, I'm going to call Uptime. Then you call Uptime and say, I want to do a 3D. And they'll say, well, what do you want? I say, well, I don't know. What can I do? Well, with 3D, the 3D card is, I equate that to a toolbox. Right? You can go a multitude of directions in the 3D card. There's a bunch of different tools, and I'm gonna explain some of the tools to you. Now, this presentation is, you can start on page 39 in the book and follow along. I'm going to hit some high points, some strengths and weaknesses of each different type of data set. Our goal here is a brief definition and history of 3D, understand the required data set parameters, what makes a good 3D, and then strengths and weaknesses of the various rendering techniques. Now, when we go down to the lab after this, we're going to do hands-on. By the way, I did call IT to take care of our simulators. They were kind of acting up this morning. So Pete has reassured me that they're working well now. What is 3D? This is a term we throw around loosely. And this is a quote I got from Derek Nye, and it basically means by which we can take sectional images and we see depth. Well, Derek Nye is the big brain at HIP Graphics. HIP Graphics is the company that writes our software for InSpace. I know I looked at the sales orders, and I think you guys got it. You guys got it as well. Derek Nye came to work from Pixar. Have any of you seen Toy Story?
Sure.
Yeah. You've seen Derek's work. A lot of the technology that we use in 3D medical imaging today came from the motion picture industry. Just a little fun fact for you there. Why use 3D? It wasn't that long ago. Those old radiologists said, I don't need no 3D, it's just a marketing tool, help me sell my diagnosis. Well, then that was probably defendable, but now times have changed. The way CT works, it just lends itself. It's easy to do 3D in CT. Computing cost, much, much better. It wasn't that long ago that a 3D workstation cost $250,000, $250,000 to do a 3D. Today, I can do on my laptop what used to cost $250,000 or more. We're finally there as far as computing goes. And then the study size. I know some of you guys, I took the pre-course survey, kind of get an idea where everybody was. And I know we got some that are pretty new to CT and then some that have been scanning forever. So remember back in the day, typical study, 25, 30 slices. We did everything at 10 millimeter thick slices. Today, we're doing sub-millimeter thick slices. A typical study, 600 to 4,000 images. We're volume scanning. And doctors need a means by which they can volume visualize all this information that we're hurling at them. They have to, it's a matter of management now. Scan and reconstruction parameters. What makes a good 3D data set? Garbage in, garbage out. Every one of these parameters in each data set has to be the same. Field of view, X and Y coordinates, gantry tilt. If any of these numbers are off by 1 millimeter, it just doesn't work. Recommended 3 millimeter thick slices or less. Everybody in this room with their definition AS scanner is capable of sub-millimeter thick slices. So this is not a problem. And spiral is definitely better than sequence scanning. Before we, no discussion on 3D would be complete unless we talk about pixels and voxels. Pixel, who knows what that word pixel, what is that? Where did that come from?
smallest element in an image.
You're right, right. Pixel is it's a combination of picture, element, pixel. That's the surface. It's the X and the Y of our image, our two dimension. And then a voxel is the slice thickness, the depth, the 3 in 3D. That's what gives us that depth perception. And when we talk about voxels, we have to talk about isotropic or non or anisotropic voxels. And what does that mean? Well, an anisotropic voxel is what we've had forever. And that is the width and the height is pretty much the same. But when we take that slice thickness, that voxel, and rotate it, you can see how it gets elongated, distorted. It's not a pristine data set. Whereas with an isotropic voxel, the height, the width, and the depth is all the same. So you have a perfectly cubed piece of data. There's no elongation, there's no distortion, so your output images are better. And then when we do our reconstruction parameters, I've got some images farther into this that will explain it, but depending on what direction we're going, we're going to have to pick the appropriate kernel. So today there's two classes of rendering techniques commonly used in medical imaging today. There's volume rendering, which is a MIP and a VRT, and then surface rendering, which is a SSD. They've all been around for quite some time. Before we do anything, reformat, any kind of 3D, this one thing happens. We scan, we get our raw data, we reconstruct those slices, and we put those slices back together and create a volume, and that volume is in the 3D card. From there we can go any direction, but this always has to happen first, and it's just by virtue of scanning it does. First up is who's using MIPS now? I know some of you got MR experience. Actually, MR invented MIP back in the day. And this is a lot of words that says we usually use it for vascular structures. Usually use it for vascular structures. Well, when we talk about what a MIP is, we have to talk about what a MIP isn't. A MIP is not a regular CT slice. Here we have a typical 10 millimeter thick slice, and we know in that 10 millimeter thick slice we have different densities. When we look at that slice, what we're looking at is an average of those densities. Who has heard the term volume averaging before? Chris has? All right. Christian, I know you have. Well, a MIP, we can take that same 10 millimeter thick slice, and what it does is it takes that densest value, and that's the value that it assigns along that line, that ray, that row of voxels. Therefore, that's what we see. So let's bring it home. Everybody in here, we're medical imaging professionals, so you should know your anatomy well enough to know that this is a contrasted study. Why can I not appreciate or see that aorta?
Too much bone.
Right here. Yes. The bone. The bone, that's the densest value, therefore that's what we see, right? So what do I need to do to that to see that aorta? Remove the bone, right? So once I take that bone out, we can see there's actually more to the story. Would have never seen that stent graft. So there's actually advantages and disadvantages to a MIP. MIP, you get superior accuracy over surface rendering. Reproducible results. We can have everybody in here, regardless of your experience level, getting the same thing over and over. And it's low cost. Everybody gets it for free. It only uses about 10% of the data set, so it doesn't require any extended memory or advanced graphics cards. It may misrepresent spatial anatomic relationship. often, like that example with the bone, we often have to go in and remove the bone to appreciate what we need to see. And it's unable to represent superimposed structures. That's why we do those rotations. MIP. So, any questions about MIP so far? I'm going to have some examples here in a little bit, but it's common, it's quick and easy. Everybody in this room has it. Vascular docs like it. And then we have SSD, shaded surface display. Again, this has been around for a long time as well. And this is a lot of words, basically, that's telling us we're looking at the surface of a volume. SSD, you cannot change the color. It's hard to window. You can't do a whole lot with it, but it is effective. And the way an SSD works is, here we have our Hounsfield scale, minus 1024 to 3071. And what we're saying here is everything at 150 or higher gets this monochromatic ceramic type display. So if I had metal clips or contrasted vessels in here, what would they look like? The same, right? Assuming they're 150 Hounsfield units or higher. You remember we talked about HUs earlier today. That is Hounsfield unit, right. That is the density numerical, yes.
Can you define, what exactly is a Hounsfield unit?
Hounsfield unit is, that is what gives us our job. It's the atom of CT. HU, Hounsfield unit, is a numerical destination or a numerical assignment for densities based on the premise that water is 0, air is minus 1,000, and bone is 1,000. So based on those known factors, we have these numerical values in between. And the scanner and our software can sense the density and therefore assign it a corresponding number. That's a great question.
Thank you.
Great question. So anything 150 and higher is what we see. So here I feel pretty confident we contrasted this guy. Would you agree? How can we tell?
The external carotid.
Right. So if I drop that value lower, it's kind of creepy, right?
Yeah.
Almost a HIPAA violation. All right. So here's side-by-side comparison. SSD, we have no density difference, but we have that 3D reference. The MIP, there is density difference kept. But what do I need to do to that? Get rid of the bone. That, my friends, is marketing quality. That's a diagnostic tool. Just again, some more side-by-side comparisons. Comparing, an SSD to a MIP. SSD looks cool, but that's not what you want to use for vascular structures. So advantages, it's low cost, low computational cost, easy to use, click, boom, you're done. Now the downside is it is not suitable for all anatomy. We use SSD for ortho work. Facial fractures, anything broken bones, spines, etc. That's its primary use. Sensitive to changes in thresholding. It's rigid. It can be all or nothing. If you use that slider too far, you can put holes in the bones. It's a term I call osteotermitis. Holes in you guys got it. Good. All right. Thank you. I'll be here all week. And then up we have is volume render technique, VRT. That is the pretty colored stuff that everybody wants. I have examples in your book. There you go. That's the pretty colored stuff. VRT uses the entire volume. Every voxel is classified and evaluated. And because we use every voxel, we can assign different colors or opacities to different densities. And because of that, we can do see-through effect. We can do a lot of really neat stuff with the VRT. There's two stages of volume rendering. First is tissue classification. That is, every voxel is looked at, it's evaluated. And by now, are we hoping we have isotropic or anisotropic voxels in there? Isotropic, right. Each voxel is looked at, the densities are evaluated, and then these colors, opacities, are assigned to all these different densities. And then the volume is rendered. Now, I like to use this data set because techs that have been around for a long time go, wow, that's pretty cool. So in this case, Ortho sent this guy down and said, I want you to do a CT of the spine to evaluate the integrity of the hardware. And what would be your typical response if you got that, Chris? You're smiling, right? Because you know it's not going to look very good. All right. Okay, doc, whatever. But because we can assign different colors or opacities to different densities, we can do some neat stuff with this. So here, what we're looking at here is a histogram. It's a graphical representation of the densities within this volume. I created this one, but your scanners will come with one default. What we're saying here is everything 1800 and higher gets this blue color. That metal hardware falls within that range. So as a result, I can window out that bone. I can window out everything surrounding. And if you look really close, you can count the threads on those screws. I worked for a place in Texas where we would scan parts for Bell Helicopter. I have colleagues in Germany that actually scan Formula race car parts. Those are expensive engines, and they're going to reuse whatever they can. So we're able to do some really neat stuff with VRT. Side-by-side comparison, SSD, MIP, and a VRT. Here, we have density information in 3D reference. We have density information, but no 3D reference. It's kind of hard to see where we're going. But with VRT, we have all three. We have 3D information, 3D reference, and color reference. Advantages. We're able to see through surfaces. We can vary those opacity values. Better image quality than SSD. I still scan every weekend. I'm at Duke, and we do SSDs we use for the craniosynostosis kids, MIPS all day long for our vascular studies, and VRT, CTA work as well.
Okay.
This is the preferred one. It can have a higher computational cost. We can have variable opacity. You can have distorted results if you start playing with those colors too much. A scan parameter question. Which one of these pictures looks better?
One on the right.
One on the right, absolutely. Why? What makes that one better than that? Huh?
Slice thick.
Slice thickness, right. There's your answer right there. That's the difference between a 1 millimeter thick slice and a 5. Now we still see step here. What's causing that? It's a little pop quiz. Yeah, Russ?
Cardiac motion.
Everybody agree? How do we know it's cardiac motion?
Heart's always moving.
Right. So if it were patient motion, we would see step throughout. If it were breathing motion, you would see that diaphragm shadowed at multiple levels. All right? Neither one of these pictures is great, but one looks better than the other. Which one is better? All right? They're both the same slice thickness. They're both the same kernel. What makes that one better than that?
It's distorted.
That's the difference between no overlap and a 50% overlap in the data set. And I'll show you guys how to do that down on the scanners, on the simulators. Have any of you ever done an SSD and got something like that? Yeah. What are we seeing here?
A lot of noise.
That's the noise induced by the kernel, the algorithm. That's using the wrong algorithm, the wrong kernel, in reconstructing that.
That's what I was doing wrong.
We use a standard or smooth kernel. Again, see that noise there? Using a high-res kernel versus a standard. And this, what rendering mode is this?
VRT.
VRT. Yep. All right. So we did the brief discussion of history of 3D. We understand the required data set parameters, and we just learned the strengths and weaknesses of different rendering modes. What does MIP stand for?
Maximum intensity projection.
Winner, winner, chicken dinner. There you go. What data sets do we usually use it on? Vascular or CTA? Awesome. All right. What does SSD stand for?
Shaded surface display.
Straight out of the book? Perfect. I don't care how you get the answer, you got it. That's okay. And what do we use that for?
Ortho work.
Ortho work. That's it. Boom. All right. I have a whole bunch of questions, but I know you guys want to get down and start doing this. So any other last questions about 3D, just the 3D basics? All right. So let's get down to the lab. You can leave your stuff here. Let's go.